Revisiting irrational numbers. In this module, you will learn about some theorems and proofs related to irrational numbers. You may know the fundamental theorem of arithmetic, which states that every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Let's learn a theorem whose proof is based on the fundamental theorem of arithmetic. We need to prove that if p is a prime number and if it divides a square, then p divides a, where a is a positive integer. Let's begin with the proof. Let us assume that prime factorization of a equals p1 into p2 and so on till pn. On squaring both sides, we get square of a equals p1 square into p2 square and so on till pn square. It is given that p divides a square. So, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. According to uniqueness part of the fundamental theorem of arithmetic, the only prime factors of a square are p1, p2 and so on till pn. So, p is one of these prime factors, and since a equals the product of these prime factors, p divides a. We use this theorem to show that the square root of 2 is irrational. Let's see how. Let us assume that the square root of 2 is rational. We can find two integers r and s such that the square root of 2 equals r upon s. Suppose r and s have a common factor other than 1. So, we divide r and s by their common factor to get the square root of 2 equals a upon b, where a and b are co-prime. This means that b into square root of 2 equals a. Name this equation as 1. On squaring both sides and rearranging, we get 2b square equals a square. Thus, 2 divides a square. Using the previous theorem, we get 2 divides a. Now we can write a equals 2c for some integer c. On substituting this value of a in the equation 1, we get 2 into b square equals 4 into c square, or b square equals 2c square. This shows that 2 divides b square. This means 2 divides b. This shows that a and b have at least 2 as a common factor. This contradicts the fact that a and b have no common factors other than 1. So our assumption that the square root of 2 is rational is wrong. We conclude that the square root of 2 is irrational. Similarly, we can prove that numbers like the square root of 3 and square root of 5 are irrational. Now you know that the sum or difference of a rational and an irrational number is always an irrational number. Let's prove a particular case. We need to show that 5 minus square root of 3 is irrational. Let's assume that 5 minus square root of 3 is rational. This means that 5 minus square root of 3 can be expressed as a upon b, where a and b are co-primes. This equation can be expressed as square root of 3 equals 5 minus a upon b. Since a and b are integers, The expression 5 minus a upon b is rational. This means that the square root of 3 is rational. But this contradicts the fact that the square root of 3 is irrational. This means our assumption that 5 minus square root of 3 is rational is wrong. We conclude that 5 minus square root of 3 is irrational. You may also know that the product and quotient of a non-zero rational and an irrational number is always an irrational number. Let's prove a particular case. We need to show that 3 into square root of 2 is irrational. Let's assume that 3 into square root of 2 is rational. This means that 3 into square root of 2 can be expressed as a upon b, where a and b are co-prime. On rearranging the equation, we get square root of 2 equals a upon 3b. Since 3, a and b are integers, the expression a upon 3b is rational. This means that the square root of 2 is rational. But this contradicts the fact that the square root of 2 is irrational. This means our assumption that 3 into square root of 2 is rational is wrong. We conclude that 3 into square root of 2 is irrational. In this module, you have learnt about some theorems and proofs related to irrational numbers.